Yeah, hello everybody, and welcome to this webinar. It's the fourth already in our series about reinforcement learning in finance. From playing games to algorithmic trading, playing games was just the starting point. So now we work through different approaches that allow us to train DQL, or as we call it, FQL agent, for financial Q learning agent based on historical data. This is what we have covered so far. Now we attack the problem and the issue, which is that we basically are always dealing with limited data, limited in the sense that we might have an historical time series that we might derive statistics from that, but still there's just this one data set and some derivations, some statistics that are derived based on that. So we face the issue that is not present when we play games, for example. Think of chess. This is my canonical example where an agent can play against itself over and over again. If it has to be like a million games and can learn from mistakes, can also learn what worked out well, right, and all these elements. And with regard to historical time series, if we are just dealing with fixed data sets, that's kind of an issue because it's kind of limited, right? It's just like one possible evolution that we use in order to train the bot or the agent. So today we enter the world of Monte Carlo simulation, where we can use the simulation approach to generate basically an unlimited number of iterations for the training exercise and also for testing, right? That we say, well, it's not just that we have some holdout data and then test it there, rather can test what the agent has learned, then also based on newly generated data sets, for example, right? That's all possible. So this is basically all based, apart from the Monte Carlo simulation that we are entering today. So this is not in the book, Artificial Intelligence in Finance. There, the space, so to say, was limited. But in that sense, we're going to build on top of what we had. You know already the basic structure. We will have an environment, we will have an agent, and then we train and test in this context. What we can do, as I said before, this a little bit more systematically in the sense of having basically an unlimited number of paths available, of data sets available when we use Monte Carlo simulation. Here you see, as usual, the overview of the resources, the links to the resources, right? It's the GitHub repo, which has been updated with 2 new notebooks. You can use Google Colab as well. So I checked, it all executes on Google Colab without any additional installs or whatnot. Of course, the Discord server is something that you should have joined, and that you should use the chat channel there in order to ask and post your questions. And of course, Twitter will also be something that you might want to follow along. In this slide deck, you might recall we have the background material with regard to the basic notions of reinforcement learning, as well as with regard to Q learning. Since we're going to review all of that anyways based on code, there's no need to go at this stage through the slides again. I said already, I have updated the GitHub repo. So you find here 07 and 08. So I changed the naming here a little bit, or the numbering, so that we now have consistent sequential numbering. And these are the 2 new notebooks that I want to go through today. So I have been asked a couple of questions with regard to what we have covered previously. And I think that when we now repeat the whole thing once again, maybe I can then go and answer or highlight the questions related to the previous notebooks there as well. Again, Colab, you have the link. It's pretty nice. You don't need to install. You don't need to take care of, I don't know, TensorFlow issues. I'm happy that it works here out of the box. With TensorFlow in the past, it hasn't been always that easy when you change version. So I can I can talk about that, for example, with regard to AI in finance. When I started, then we had like a succession of different versions where I always needed to update it. And previously, again, there was a need to update the code. So what is printed currently is slightly out of date, but what is found, for example, for AI in finance on GitHub, it works now, I think, out of the box. Should also work with Colab, for example. Yeah, let me dive here into the notebooks. 07. Maybe here and there I might use my classes when we dive into the details. And you know, I might be looking regularly to my left-hand side in order to see whether there are questions that I can answer in this context. Yeah, our starting point, as usual, a bunch of imports and a bunch of configurations. With regard to TensorFlow, also some typical things that I use here locally. For example, eager execution is disabled. Importing here also Keras. I don't know why I'm not importing Keras from TensorFlow. I don't know. Let me do that. Do I do this above? No. I don't know if this makes a difference. If it doesn't work later on, I will take it out again. Import Keras shouldn't make that much of a difference. So setting seeds, you know, with TensorFlow Keras, it's always a little bit tricky to make stuff reproducible. It's not, I would say, completely necessary to have it reproducible, but in some instances, of course, even when you work with yourself, with the code that you've changed yourself, it's of course good to have some means to fix the result and to see how something behaves ceteris paribus, so meaning everything equal. Because when you change, let's say, a parameter and everything is random still, it's pretty difficult to figure out what the effects might have been given your change. So Q-learning, we have the DQL agent, and the DQL agent, it's, I would say, well known. There is now nothing special. It's basically what we had before. I have just changed here. I'm allowing now for epsilon decay to be changed. So I set it by default to 0.99. We're building a model. This is pretty simplistic here. Dense model, right? Sequential model, nothing special, no dropout, no fancy stuff, just 2 hidden layers and a couple of hidden units. So basically a pretty small dense neural network, deep neural network, we can say, because we have at least 2 layers here in this context. You know, we have 2 ways of coming up with an action. In our context, it's a prediction, it's an action, right? Market goes up, market goes down. The one is exploration. This is just a random sampling for the action, so no intelligence, no policy whatsoever. Or exploitation, where we rely on the neural network in order to come up with an action in this context. Exploration, you know, and you might recall, is necessary so that the agent has enough experience and enough diverse experience in that sense to have a policy which can deal with more than just maybe a couple of special cases. So in other words, the agent shouldn't specialize too early and shouldn't believe that it has already covered all the bases. The replay is for the training of the agent, where we do the recording, updating. You know, this is a random sampling here of our memorized experiences based on the DECQ. A list object, which is limited, right? Works like a queue, so that we just have recent experience there on which the training is based on. We sample like 32, I think is the number, right? Experiences, and then train, retrain, update the agent. So the learning is, of course, the core. Everything else, if you like, is just helping. It's just getting flesh to the bones, but here we have the core algorithm where the agent, so to say, plays over and over again. And playing here means, of course, trading, or if you like, it's a prediction game, right? Where you say, well, the market goes up, market goes down, and we have certain criteria that we have seen already. Maybe it's an accuracy or a certain performance level and as long as the minimum thresholds are still valid, so to say, are not broken by the agent, then the agent can continue until the data is exhausted, right? That's here our end. If there's no data left, then that's it. You see here now the environment that's initiated. I come to that down there. You see this environment now is quite a bit different to what we have had before. So when we do the simulation, I have created here an environment which allows the passing of a number of parameters. And what I'm using here is an Ornstein-Uhlenbeck, so mean reverting process, which I can parameterize. Based on this process, I can create a model, so to say. I can create trending processes or mean reverting processes. So this gives us a kind of flexibility, but more on these details further below. And the rest here is kind of like the same that we had before. So now simulation environment 1, which indicates that we might have simulation environment 2 as well. Our mock-up classes here for the observation space and for the action space, and then we have now this simul environment. And now maybe we can go through the parameters. First symbol, this is now just a placeholder because we're going to simulate something, and this is just to give the baby a name, if you like. It's not really necessary because this is at this stage all completely random, given the parameters that we pass afterwards. So features, we can then select features that will be used and will be returned. Steps, and the so steps means how many steps you would like to have. With our historical data sets, we have a fixed number, right? Maybe we have, I don't know, 2,500 data points, but here we can say simulate 350, 100, 250, 2,500, 10,000, 25,000, right? We need to be a little bit careful with regard to the scaling. So what I assume here is 1 year, and I will have the 1 year frame, so to say, in the background, but this can be adjusted later on. But there's one point, you see it here, where I say DT1 over self number of steps. So this would imply here basically that we think in terms of 1 year, right? So 1 year as a default assumption. Since we're not really interested here in some form of discounting, or we don't have here a let's say deterministic component for the drift here, right? No, let's say short rate that is relevant. That's fine in this way, but this could be done a little bit more sophisticated. In particular, if you want to have another difference equation, another model for the process, then this needs to be taken into account. And then we have the parameters. X0 here is the starting value, kappa, theta, sigma, and these are the other parameters, right? Theta is a long-term level. It's assumed to be 100. Kappa is the mean reversion factor, so that's the strength with which the process moves back to the mean, to the long-term mean theta, and sigma is, like with geometric Brownian motion, Black's codes, is the volatility factor, right? And these are the parameters that are used down here. So self kappa, that's the mean reversion factors, self theta, that's the long-term mean, and we have self sigma here, which is multiplied by the dt factor here, or square root of dt with the standard normally distributed random numbers that are drawn here step by step. So, and this process, which is kind of simple, standard in financial engineering, mathematical finance, allows us, as I said before, to simulate different behaviors, mean reversion, or depending on the parameter constellation, also positive trends, negative trends, This is what we can basically model, so that we then have a little bit of flexibility in order to say, well, agent, are you able to learn that, for example, this is positively trending over time, or that this is negatively trending, or that there is some mean reversion going on? Can you recognize this? So it has its limits the approach, but I think it's one possible starting point in order to circumvent the issue of just having 1, 2, 3, 5, 50 time series. Here we can have 500,000 different time series that we make use of. So the rest here is related to the data handling, normalize, and whether we pass in here the factors for the normalization itself. So we have 3 of them. It might be none, or we might be passing here something. And I think, given what we've had before, there's now afterwards not that much of a difference. So the minimum accuracy here is set to 52.5%. I think previously I've had this a little bit lower, so even be below 50. So here I put it on a relatively high level, but we can change that. You can change that when you play around with it. I think that's the beauty of having such a blueprint. Once we have done the simulation, we do data preparation, similar to our fixed data sets, right? If there is normalization going on or not, right? And then we get the state, and state by state, or bar by bar, technically from a numerical point of view, we then pass the data to the agent, and the agent has the main task here in this context to predict whether the market goes up or down. Right? The reward is simple. If it's correct, it's a +1. If it's incorrect, it's 0. So this is again more or less in line with where we got started with the card pool. But now we have something that is, at least with regard to one respect, closer to the card pool world, in the sense of that we now have randomness in basically everything that we do. Of course, we could fix it based on the seeds, but that's of course not the idea here, to fix everything and to do it over and over. This is where we're coming from. So when I do, for example, 10 different trainings here, for example, I can work with different data sets, but that's something for the next Jupyter notebook. So that's the environment, random simulated data. Again, I will use some symbol, what we had before, but the symbol here has no relationship to real world data or whatnot. This is just to give it a name and to have maybe some idea. So having talked about symbol, here I get started maybe with scenario 1. Let's have a quick look at the scenario. So scenario 1 is a baseline scenario with a price feature, then a trend scenario, a mean reversion scenario with a price feature, and a mean reversion scenario with a return feature. So here we are still in a rather simple world, and it's even made more simple here with the very first baseline scenario, which is basically a deterministic one. So I was talking about simulation, and that this is the whole approach here, but I set here the volatility to 0. And what I want to first check is whether the agent in this very simple baseline scenario, simply some, let's say some deterministic increase, as we will see, is able to figure this out, and how long it takes in order to recognize for the agent that, oh, it's always going up. So I always predict here a +1 or an upwards movement, right? That's just a little check in that sense, our baseline. And with the second scenario, trend scenario, right, then we introduce here volatility, and this will be random. But we will see this visualized, and I think the pictures that tell then the whole story much better. So such an environment now, data hat, right? You see the values here already for the first couple of them. They are increasing deterministically, and the R in that sense is always positive, right? So when I have a look at the value changes here, we have 364 +1. So it's always going up. That's our baseline scenario. and this is how it looks, the data, right? Like, it's not linear, obviously not, right? But it is at least strictly increasing. Sample enter rest now. The whole environment behaves like our very first environment from OpenAI Gym, Carlo, and all the other environments that we have used so far. So let's see whether the agent figures this out. So we set the seeds. The DQL agent is now parameterized. All these values now do not really play a role. I just want to list them here. Gamma can be chosen, hidden units, and the epsilon decay, just to have them explicitly here. Number of episodes 250, and now let the agent learn. So it's not obviously from the beginning the case that the agent notices that, because we still have exploration, right? But towards the end here, pretty quickly, you see that the average now is 361. So the agent here learns pretty quickly that it's going up. So in between a couple of maybe random explorations, let the average drop, but towards the end, well, we have still epsilon, slightly below 0.1. We have something like a plateau, but you see the agent learns quickly. Here it goes back. This is due to exploration. Here it is plateauing on the highest possible level, then dropping back a bit, and towards the end, nothing happens anymore. The agent has finally figured out that always saying +1, +1, +1, or upwards here is the right thing. We can test the agent, which is now, of course, pretty simplistic. It always gets here a perfect result. If you like, you can also do the same exercise with theta going down. So not theta going down, set theta below 1, so that the deterministic process goes down, right? We always have now negative returns, right? This is in this column that we see here. And we can train the agent in the same way. And it's pretty quick here that it learns and recognizes, oh yeah, that's kind of like always going down. So whenever I say 0, 0, 0, I'm on the good side here. I'm getting the rewards. So I could have here a break condition, for example, like with Carlo, where I say, well, if the average reaches 361 or 350 or whatever, breaking it, but this wouldn't make that much of a difference. So here you see it reaches just before 150 episodes, it reaches the highest level, and from that on, nothing happens anymore. That sense, of course, here, perfect result. But that's baseline, that's simple, right? Maybe I'll leave it here with the 1.1, that it's going up and the agent becomes a long-only investor in this context. Yeah, this is pretty nice. I would say towards the end perfect, but of course it's a very simple case, right? It's like a absolute simplistic math problem. If it's not that challenging, we shouldn't be too happy, right? And we see here, no matter whether we draw now another quote-unquote random simulated process, it's basically the same. So that's more interesting when we have randomness included. And we can do this now by changing here the scenario to 2 in this context. Well, maybe let me check here as well. No, there haven't been any questions in the meantime. So scenario 2 is now a trend scenario where we work with the price feature. And the next one is a mean reversion scenario with the price feature and then the return feature. So let's have a look. Now we have randomness, right? Here we see it. and it goes up or goes down, right, depending on what has been drawn randomly. And although this is representing a positive trend, we nevertheless have also negative movements, right? But here in these scenarios, usually we are dealing with, when there's a positive trend, we are dealing with a situation where we have more upwards movements than downwards movements. This is reflected here in these values. So when I reset the environment, now the randomness again is demonstrated when I step the environment one step forward. Again, that's now the random data. So let's see how the agent does in this context. 250 episodes. This is not as simple, but for us human beings, we would say, yeah, of course, this is positively trending. I can't do anything wrong when I'm a long-only investor here, but there are still like shorter episodes here, for example, where the price comes down. So it would be beneficial to go short here or to go short here towards the end. It's beneficial, but overall, it would be a good policy to say, well, I go long because obviously the investment increases on average in price. And you see, this is now almost a linear curve for the agent with regard to the total reward, right? It's not perfect at the end. Let me see what the last, the maximum was 361, but the average towards the end was 313. Not yet perfect, but pretty good in this context. And when we test the agent, yeah, 6 is for sure not good, but all the 361s here, they are good. When this is what I meant before with the deterministic scenario, there is no real case or benefit in comparing the base simulation with the second one, but with the same parameterization now, with a different starting point, a different seed, you see that a second drawing gives me something similar, but not exactly the same, right? Blue is what we had before, and green is now a second one. They are pretty close together, and the agent, if it has learned that, oh, well, what I'm faced with here is on average upwards trending, then the agent shouldn't have that much of a problem with the green one as compared to the blue one. So training on the blue one should equip the agent hopefully well for the green one here. So this is what we have done with regard to the testing. So this works to some extent and can of course be refined. We are still dealing just with one feature, currently the price feature, and only 4 lags. So this is still in line with our original setup, starting with a card pool gaming environment. So scenario 3. Now it's getting a bit more interesting from my point of view. And I should probably say I have illustrated this with the changing theta before, that I could also create something that is trending negatively. So when I have here the second one and set theta to 50, let's say, then we get something that is negatively trending. So see, it's pretty simple and straightforward to do all this here with the Ornstein-Uhlenbeck process, the mean reversion process. I could also, if I like, for example, add volatility by saying here 50% instead of 25%. So this makes it now. You see the volatility now has dropped it here sharply, and then it's positively increasing. So theta and volatility here are core factors. Also, of course, the kappa, the mean reversion factor, if I increase this to 10, let's say, I can straighten this out quite a bit here. So I can only recommend that you play around a little bit if you haven't done so in your recent past maybe, with these parameters. But once you internalize the effects, what the different parameters have ceteris paribus, and therefore it is good to work with a fixed seed in such a context, that you see, well, it's not randomness that has changed here, something, it's just like the parameter. Then you get a good feeling, and you will recognize and see that you can model at least a couple of interesting scenarios that traders are typically interested in. So I might be going back to my original ones, year 1, and this was 500 positively trending and 25%. And now to the mean reversion scenario. With the price feature only 100 is a starting point. Kappa is set to 7.5. It's pretty high relative to the 1. Theta is set to 100, so this is starting at 100, and long-term level is 100, and sigma, the volatility, is relatively small compared to the 25% that we had before. And the feature is just the symbol down here. It will be the return. So let's see, and this is now the evolution. So it's hovering around 100, but there's no guarantee that towards the end of our single simulation here that it will be close to 100. It's just, I would say, for the first 80%, and then it drops sharply. But I'm not fixing a seat here, right? So when I repeat the exercise, this now looks different. So I was just watching out for a line of code where I might be fixing the seed. So this is now simply another draw, another simulated process data set where it's a bit more obvious, because now it's not too far away towards the end from the 100, which is a long-term level. And if we would go, I don't know, 500 steps more, for example, then we would see the mean reversion factor. But here I think it's already pretty well illustrated, right? So the rest, as they say, remains the same, and we can now train the agent based on our environment. And the idea would now be that the agent somehow recognizes that this whole thing is hovering around 100. But you see, this seems to be a difficult thing, because the average, so by chance, it once got to the end, 361, but the average is just 12. So this is for sure not as good as we have seen it already before. And all the tests here for newly drawn processes indicate, yeah, that's not something that we should be happy about. But there's one thing when we have a look at this here. Do I know? In the other one, I'm calculating the correlation in the other notebook. But here they can be pretty similar, but they don't have to be, right? So meaning that what I said before, with a positive trend, no matter whether I draw 1, 2, 3, 4, 5, 7, 10, 2000, they all look basically similar. But here we only have mean reversion as one characteristic, but the rest, they can be, the two processes can, to put it in other words, can be highly positively correlated, can be highly negatively correlated by chance, there's nothing by construction, or can be not correlated whatsoever. So everything here in the correlation from -1 to +1, everything is possible. Therefore, it's a little bit more tricky for the agent, so that's a difficult task. Maybe we can say, well, let's learn it a little bit longer, let us train it more. But you see, well, there's no real improvement, still like one thing. And you see, this is hardly coming out of the basement, so to say. No real improvements here. Maybe the price feature is better, right? Mean reversion, returns, maybe with regard to the returns, it's better to learn, because maybe we have like a couple of positive returns, and then it learns, recognizes, and predicts that the market might go down a little bit better than just based on the price level. Also, normalization, a couple of other issues could be discussed here. So therefore, 4. Right? This looks now almost the same, but it isn't, right? It's something else now. It's just these are the normalized returns, right? Before we had something around 100, now we are dealing with the return, so we need to be careful. The agent, I stick to my parameters here, so quite arbitrary. really. And now we see already that the average is increasing faster and better. So, I mean, it's not 200, it's not perfect, but still, before we were hovering around 15, 16, what did we have there? Like for the test, 25, 8, 7, 12, pretty low one digits or 2-digit values, but no triple digit values, right? So let's see how this looks. And with the returns, it suddenly is able to somehow recognize mean reversion and to learn at least some structure, which might be helpful to predict this, right? Not perfect, again, it's not like a straight line going upwards, but still, we end up here at a level of 200. And when we now do a test, so let me copy these here, that we can compare. Not all of them are good. Maybe this can also be due to the fact that I mentioned before, like 52.5, right? Where I have set the bar pretty high, but some of them now go through, quote unquote, here 174 to 08. Can also be the case that we have to deal here with some overfitting, for example. Right? So let me train it once more. You see exploration already is pretty low already at this stage. Because maybe I should emphasize that, although we simulate here and include for the first time randomness, if you like, it stays the same process. So I just have one process in the environment and it is not changed whatsoever, right? So maybe this is worth highlighting. And here you see towards the end, yeah, it's not like now going to 361, right? And the here you see a typical effect of overfitting. It's now worse than before on the test data, right? And again, what I was saying before holds true here as well. We now have something which looks more like relatively highly negatively correlated in this context, but I don't want to go into these elements because the next Jupyter notebook provides us a little bit more flexibility in this regard. But at least I think there's a good, from my point of view, it's a good starting point that we say, well, it's not just one time series and we go like over and over and over it again, change parameters, hyperparameters. At least I can here manually set different Cs or create another environment and then train the whole thing on another process and see how it works. We have seen in the beginning that mean reversion with the returns feature is something that the agent can learn about, but we want to maybe get a bit better in this context, right? So speaking of better, the other notebook that I've prepared and already shared here has the same starting point. So I now want to highlight primarily the differences to what we had before. Here I'm importing Keras from TensorFlow, and the other one I have in simulation environment 2. So what are the differences? Let us have a look. Symbol features: window, it's new. Lags can be changed. Number of steps as before, like 250, 365, 1 year. The process is the same, x0, kappa, theta, sigma. I can include leverage here. The minimum accuracy can be changed, the minimum performance. Here, now you might recall this, in addition to the accuracy, we now introduce a performance measure. So we don't allow the agent to drop or to lose more than 15% in this context, right? And we can use data and slice and dice it. So here with the starting point, an endpoint, mu, standard deviation, normalize as we had before, and renew. This allows now that when it's a flag, this allows to again improve a little bit on what I've said before, whereas well, once we have drawn or simulated the process for the one environment and then I train the agent like 250 steps, 500 steps, it's always on the same simulated process. It's just one data set Okay, it's randomly generated, it's simulated, but still it's just one. And here I now include the option to resimulate, to create a new simulated data set every time the environment is reset. So what I was saying before, like 250 episodes for training on the same data set, now I can set the flag and can say, well, the agent can be trained 250 times, and every time the data set changes, so that the agent now we are getting into the world of playing games, right? We say, well, a chess game is always like different. Maybe an opening might be similar or something, but a chess game from start to finish typically is completely different. I mean, alone the number of options that are there, right? They somehow ensure that you have a different game every time you play a new. If there is at least some element of randomness, of course, when you have two computers playing against each other, if there is no randomness whatsoever included, then they might be playing the same game over and over again, right? But here I now allow, instead of 250 episodes on the same data set, 250 episodes on different data sets. So that we say, like with the trending scenario from before, we have stuff that is similar, but not exactly the same. And I think this comes close already to the saying we should filter the signal from the noise. So the trend might be something that is common, but everything around the trend, this is what we call noise, right? We have noise here. We have one element in the simulation which is standard normally distributed. So this is typically what is called white noise in this context, right? So the rest, let me see. Leverage is not that relevant here for us. That's for when you say, well, I'm trading, I don't know, CFDs or leveraged FX positions. Minimum performance, as I said before, this is now checking what the performance is given the correct or incorrect predictions. Anything else? No, here's the simulation. That's kind of like what we had before. Maybe we set this to, I don't know, 22 and 23, so a little bit later. But this doesn't change the whole exercise. And here for the, whenever I have a window value of greater than 0, then I create 5 different features. And here you can, for example, add your own features. So if you say, well, I'm a big fan of relative strength index or whatnot, you can add this here. I'm sticking to the basics here for illustration. So I have a simple moving average, then I calculate a difference, meaning the current value in relation to the simple moving average, a minimum value, a maximum value, and a momentum value. I could also work with volatility or whatnot, with whatever comes to mind. But here it's a little bit targeted towards the mean reversion problem, in particular the difference thing. So maybe the agent learns, that's the idea. When the difference is pretty large, that probably the market or the asset here goes down in price, or where we have a negative difference, let's say -10, then the agent might learn that probably the price goes up in a mean reversion context. What else do we have? I think the rest is more or less the same. And here you see when renew is set to true. No, I have out one. When new is set to true, then I go and simulate and prepare the data again and again. Otherwise, if renew is false, the behavior is as before. When I train for 250 episodes, it's the very same data set that is used for the training, not for the testing. Stepping here, so I work with a reward now of 1 for a correct prediction, 0 for an incorrect one, and I have a factor here of 100 times the PL, and the PL is the absolute return if it's correct, and minus the absolute return if it's incorrect, something that we have discussed already before. So 100 or 250 or whatever you want to have, This can be debated. We could also go with +1 and -1. We have many options, and I think I said this. And that's also my experience, that reward design is more an art than a science. I don't think there are really strict rules that we should follow here in this context, but something that is worth playing around and tinkering around a little bit. And the rest, should be the same as before. But okay, we have a major difference. We have now the option to have more features, right? And we can lag the features as well, right? So this is where we have here the number of lags. So symbol is only symbolic, as pointed out before. Euro, yes, dollar. Now the environment, I go now with the symbol itself and R, so I can use now two features. Window is set to 20, 4 lags, 365 steps, so parameterization here, 100 starting point, mean reversion factor 2, long-term average 300, and sigma set to 0.2. So now when I go here, I see starting values for the price itself, the returns. That's now, as before, a positive trend, right? When I go with a reset, you see now 119. This was 117. So since I have said renew, whenever I reset the environment, and this is like with card pull, when you recall that, the reset doesn't bring you to the exact same parameter combination that you got started with previously. It just gets you to another somehow similar starting position of the pole, etc., but with some randomness included. And this is what we do here, right? Moving this one forward. So the FQL agent now, of course, needs to be able to process all this. And there was a question and discussion also on Discord with regard to the number of features and the number of lags. And here with Keras, it doesn't work with MLP when you get back to the previous notebooks, there Keras and MLP. With Scikit MLP regressor, I need to flatten out this, but here with Keras, I can pass in as the input shape something that is two-dimensional, so the number of lags and the number of features, right? So that I have a set of, let's say, 5 features and 4 lags, so I have a total of 20 values that serve as features. In scikit-learn, I would need to flatten this out, so I have one vector, if you like, with 20 values. Here I can have like a two-dimensional array where we see it here, right? Something like this. It's two-dimensional. My example was 5 and 4. Here it's 2 and 4. So we have 4 rows and 2 features. 4 is the first element of the shape. 2 features is the second one, which is the number of columns. And this is something that we can pass directly into the Keras network if it is correctly defined. So we go then here with the option to have drop out or not to avoid overfitting. And the output here, the output layer is a dense layer with 2 options, because no matter how many features, how many lags we use, it's still the problem of predicting whether the market goes up or down. That's how it is here. So we enrich the feature set, but our labels basically remain the same and what we want to predict. So what else? Act, nothing special. Replay, nothing special. Learn, also nothing special. That's the FQL agent, which takes care into account the performance and all the other elements that we had before, but now based on the enriched simulation environment. And yeah, see also here for the testing, it creates new new simulated processes over and over again. So now in this setup, when I go with renew true, then the training happens on over and over newly simulated processes, and the testing also happens based on new processes in this context. Now the baseline scenario in this context, let's check features, just the symbol, so no risk whatsoever, and this is like as before, sigma 0.0. Just like, yeah, baseline in the sense that we go back to the starting point, and of course the agent and the environment should be able to do a bit more. So reset, and I calculate here the passive benchmark performance. So this is like a 6% plus over the course of one assumed year in this context. There's only upwards movements, nothing else. When I plot now the performance given the returns and the evolution in normalized fashion, right, we see that this is yeah, on top of each other. If we would have some window or what, there might be difference, but the window is set to 0 and sigma is set to 0. This is the constellation where we get this output. So training the agent shouldn't be that much of a problem. Oh, I haven't executed the most important cell here. Training the agent, 24 hidden units, learning rate of 0.001, and the environment from before, and just 60 episodes. Shouldn't be a big deal. We also get here the performance values, right? And epsilon is still at 0.55. This is how fast basically it increases. It levels out already here. And that's the performance. This is still like with regard to the performance, because we have exploration, right? And then it stops in between. This is where we get here like too low, and then it stops. When we test the agent, hopefully, and yes, we see it, 100% accuracy, and the performance is like, we get everything that is there without leverage, etc. It's just like plus 6.21%, and we get this 5 times. So that's the result here. Not that interesting, but I like to have these baseline scenarios so that I see that although I have changed quite a bit in the code and in the setup and the architecture, the baseline still goes through. Now the trend scenario, just with the symbol, maybe to get started with features, simple window now 20 lags, steps, kappa sigma. This is now yeah, closer to what we had before. Minimum performance is set pretty low, right? But this is something that we can of course change on the fly. More positive movements than negative ones, right? The passive benchmark performance is 2.59. So here I compare this again. So this would be when I simply go long, and the question is, can the agent now do a bit better than long. But when we go with, let me check, normalize. I don't do renew here in this context, but we can do this, of course, later. But let us maybe train it first without a renewal. So now, without renew set to true, it simply trains on the same data set over and over. And this looks kind of okay-ish here. Oh, this is kind of like nice. We got like a pretty good performance towards the end, but this looks more like an outlier. Maybe we train it for another 100 episodes here. It's fast enough, doesn't take too long. Small data set, small deep neural network. And epsilon now is at 13.5. And you see, still it is improving. But again, it is on one and only data set, not like with the resimulation per reset. You see the performance here is pretty variable. So there are now even better outliers like 4.5 here, right? But on average, it goes as well up. So let's test it. And the test is now based on some other data sets. So the accuracy here, it's not too bad, 60, 62, 57, 52. Performance, impressive, right? And I have here for, what am I plotting here, like 2 different simulations. We see here the correlation pretty high. So for the 2 of them, right, the correlation is high, and in that sense, when we do the testing here based on the same parameters as before, and we have this strong trend, this seems to be pretty easy and straightforward for the agent to learn. You see here performance 3.5, 3.0, 2.1. There's no guarantee that it always works that way, but this seems to be not too difficult. And we've just been working with the single feature here, the price feature, to get a clue of what is going on. So for me, the mean reversion one would be more interesting. And here I might go with 2 features, R, which is simply the log return, and diff, what I highlighted before. So diff is the difference between the current price of our fictitious asset and the simple moving average. So again, the idea would be that if this is highly positive, that it goes back somehow, right? If it's negative, then it should go up. So this should be a good indicator, at least to a certain extent, for the direction. If it's positive, the direction should be negative. If it's negative, the direction should be positive. So that would be the idea, if not the definition here of mean reversion, right? There's a question with regard to will a GPU make it faster. So here what we do is really small size. So I wouldn't expect, maybe it would be even slower on a GPU, given what exactly I'm doing here, because we have small batch sizes, all sequential. So the overhead of getting the data and doing the training on a GPU probably eats up any potential benefit for the training step itself. But of course, I'm not saying that reinforcement learning wouldn't benefit from GPUs, but the way all this is set up here, tiny, this most probably wouldn't benefit. So mean reversion scenario, similar to what we had before, 7.5, strong mean reversion factor theta is equal to x0. And we now have the full-fledged columns there. So the columns are generated, but I'm going only with the 2 of them. So I could use minimum, maximum, momentum, etc. Not D, that's what we need to predict. And when I reset it, I get now 4 rows here because I go with 4 lags. Of course, I think I don't have an example where I have some more, but of course I could go with 8 lags here as well. And in this context, the upwards and downwards movements are balanced, almost 50-50, what we would expect for a mean reversion process. The passive benchmark performance here is slightly negative. And yeah, this is just to check that the returns and the data itself, when we normalize it, are exactly on top of each other, so that there is nothing going wrong with the calculations or whatnot. So now let's see how the agent does here when we train it. 250 episodes, so the average is increasing kind of quickly. These might always be here when we get early, like a maximum, which is already the optimum. This can happen based on exploration, right? It's like a lucky punch, if you like. But we are more interested here in the average. And it's pretty variable. There's a high variance that we see here with regard to the results. So it's not that. Let me check what I've done with the. Here you see I have set a renew to true. So contrary to what I've highlighted before, now in this context, the agent is faced with another data set, another randomly generated simulated process every time the environment is reset. So it's not like the issue that is indeed problematic. in this context, or particularly problematic, that we just have one data set. This was the critique in the first place, working with historical data. So we now do one simulation and then reuse it over and over. It's basically the same issue, but with random data. Here, the training now is happening based on, always a fresh data set, if you like, right? And the performance is highly variable at this stage, right? So it's not yet able to figure this out completely when we do a testing. In between, there's a good one, that's a perfect one, but the others are not that good, right? So the performances here, I think they are all better than the benchmark performance, but still not good. And this is what I wanted to highlight before. So when we have a mean reversion quantity, this can be highly positively correlated, highly negatively correlated, or it can be not correlated at all, everything in between. So it might look like this, but another, let's say, testing process might look completely different with just one shared feature of mean reversion. So we might go and train it for another round. And you see, for the whole demonstration here during this webinar, I haven't changed the parameters such as the hidden units, or haven't touched the structure of the deep neural network whatsoever. I haven't changed the parameter here. Of course, all these hyperparameters could be changed as well. You can do some hyperparameter optimization and see what works maybe better than the base parameters. But I'm not here in the business of coming up with a perfect agent in the end with the data that we generate here. I'm rather in a business, and this is how I see what we do anyways at the Python Quants when we do training, to provide you with blueprints that you can use, with frameworks that you can use in order to then get started with your own research, your own digging deeper into the single details, and maybe coming up with something based on your data sets, on your parameterizations, on your ideas with regard to the features that might work much, much better, or might not only better, but reliably and robustly in practice. So you see, this is pretty difficult here to get this to a good stage, because every time the agent, here you see now another example. This is now, before the correlation was plus 0.28, and now it's negative minus 1.8. This is my point from before, now illustrated based on these two values. Of course, to make the training better and a bit more systematic, I can go here and put this to false, so that we can fix this one data set and at least train the agent on one data set and say, well, maybe sometimes it might be better to master one thing instead of like not having a clue about many things. We can check this out, of course. And you see, of course, the performance here immediately is better when we just have one time series simulated and the agent is faced with the same problem over and over again. This is like playing one chess game over and over. There comes the point when you recognize, even if it's a game with, let's say, 80 moves, where you fully recall every single move of white and black, and this is basically what we do here, right? But this doesn't help you in generalizing it in general, in particular with regard to chess, right? If you just recall one game, this might not really help. But of course, the neural network here has built in by default some generalization capabilities, because once we have the neural network, we still can feed it other data and can see what the network, what the policy says, and how it fares with regard to other data sets. So this now looks much better. No wonder, my example, one chess game, easy to remember. Also, the performance here is on average going up, and with exploration still highly variable. Let's see now the testing, how it works. Now, with regard to the testing, you see this is more like the overfitting issue that we have, although I don't know what was the benchmark performance. Sorry, because I have only I had the old number. In the back of my head, it was like below 1. Here, it's the benchmark performance with plus 3%. So everything here is now basically worse, right? So we see the blue one is the original data set, and the green one is one of the testing data sets, right? Yeah, but again, you have now a blueprint where you can use the color simulation, where you can refine the agent and maybe improve things in a way that the agent is able to learn in this synthetic sandbox environment everything that is there to be learned about mean reversion. We saw the learning of a trending game, if you like. This seems to be straightforward and more simple, but with regard to mean reversion, maybe a little bit more needs to be done in this particular context. Yeah, in that sense, let me check. I don't think that we have open questions left. In that sense, I wish you happy reinforcement learning with Keras, TensorFlow, and now based on our FQL agent, which gets access to simulated data. And now we have no limits whatsoever anymore. But you see, it's still kind of like, how should I say, limited in terms of the scope, in a sense that, of course, it's synthetic data, and we need to have some component where we add market input to it, right? Of course, it's nice to learn about trends. It's nice to learn about mean reversion, but it's still far from real world data. So one way, for example, which is the financial engineering way, when you would like to do a market-based valuation with such processes of options, let's say, you would calibrate the parameters to real world. That is, say, well, we have chosen out of the blue kappa, theta, sigma starting value, right? Where the starting value is the most unimportant one. But kappa, theta, sigma, these are important factors. And when we can back out these factors from liquidly traded vanilla options or whatnot and have proper factors, then we can simulate in line with the market, at least, random processes. You can say, well, this is how the world currently looks like. Kappa is, I don't know, 5.5 and theta is 7.77, making up numbers, and the volatility is 0.15, where we can back these out, like with model calibration and financial engineering. Then we have at least something that connects our simulated processes with reality, all right? But this is nothing that is currently implemented here in the notebooks that I've shown today. You have access to all of that, what I was showing today. If you're playing around with it and get some good results, please let me know. Or if you face issues, please revert to the Discord server and post your questions there so that everybody else has also something from your questions. In that sense, see you in the next session. Take care. Bye-bye.